Good morning. Welcome to the second week of virtual OTEC. This is Victoria Beal with the Ohio LTAP Center, and I'm going to be your tech support behind the scenes this morning. This is session number 17 of virtual OTEC 2020. The session's title is Developing Hydraulic Research. I have a few housekeeping items before I turn things over to your moderator. First off, questions will be accepted through the question box throughout the session. This is the same as the sessions you were on last week, but if this is your first time joining us for a session, please feel free to look for that question box in the GoToWebinar panel and drop a hi or hello in there so we know you've found it. Next, we would like for you to know that the session is being recorded, and if technology cooperates, we will post a YouTube link to a video of this session on the OTEC site once the conference completes. This means after the end of this week. Also, you'll be receiving a certificate once the conference completes for 1.5 CPDs for your complete attendance at this session. If this session runs over, the certificate is not going to be modified to include any additional time, but we definitely encourage you to stay on. Just understand that there are going to be no additional CPD credits given if the session runs over, so please don't email and ask for that. And again, the certificate's going to be available after OTEC itself has completed. I want to thank you for your attention, and now I'm going to turn things over to Becky Humphries.
Good morning. Welcome to session 17 of OTEC. I'm Becky Humphries from ODOT's Office of Hydraulic Engineering, and I'll be moderating today's session. Our first speakers are Jeff Syar and Marta Sitek. Jeff Syar is currently serving as the Office Administrator of Hydraulic Engineering, the Ohio Department of Transportation. He has been in this role since May of 2011. Prior to this position, he served as the Digital Mapping Manager with the ODOT Office of Aerial Engineering. He served as a hydraulic engineer in the ODOT Office of Structural Engineering from February 2002 to June 2006. Prior to employment at ODOT, he was a design consultant from June 1996 to February 2002, where he performed roadway, railway, and bikeway designs with an emphasis on hydrology and hydraulics. He is a graduate of Ohio with a Bachelor's of Science degree in Civil Engineering, and he is a registered professional engineer in the state of Ohio. Dr. Marta Sitek has been a part of the team of researchers at Argonne National Laboratory's Transportation Research and Analysis Computing Center since 2014. Previously, she worked at Warsaw University of Technology, Faculty of Civil Engineering as assistant professor. She has participated in various projects that covered finite element method modeling of structural response to static and dynamic loadings, and computational fluid dynamic modeling of hydraulic engineering problems. Jeff and Marta will be discussing ODOT research on the hydraulic efficiency of ODOT drainage structures. So I'll turn it over to Jeff.
All right, good morning. Thank you, Becky, for the introduction, and thank you for the attendees. I see the number has stabilized around 450, which is probably about double what we would normally see at an OTEC session. So thankful for that in this virtual world. So today I'm going to split this talk up with Marta Sitek, and she's the PhD researcher at Argonne National Labs, and she's going to do a lot of the heavy lifting. I'm going to talk more about the background of how we got to where we're at with pavement drainage, and this discussion is going to talk about the history of ODOT pavement drainage and some of the things that we found and why we're doing research to try to investigate it. Okay. Oops, too far. Okay. Well, we're going to cover a little bit of basics here. When I talk about pavement drainage, I'm talking about roadways that have curb. Okay, and in Ohio, it's going to be either a curb with a shoulder or it's going to be a curb and gutter situation. And our catchment structures is really three types. There's a graded only catch basin, there's a paved inlet, then there's the combination graded catch basin with a window. And that last one is going to be the focus of this presentation and what we're looking at. And really, the background behind this, we had a couple years ago, we had discovered that one of our grates that we had been using on one of our barrier median inlets wasn't the area of opening that we had been specifying on our standard drawing. And so I said, you know, not a big deal. Let's go look at the impacts to the hydraulics. And that's what really kind of prompted this whole research idea, because we found out that we really don't have a good understanding of our catchments and our grates and our openings and all that. So, all right, going to continue on with a little bit more basics. You know, what we designed for is spread. And the spread is based on the hydrology, which generates the incoming discharge. It's also based on the geometry of the gutter and or the efficiency of the grate. And a couple of concepts that we're going to throw out there are frontal flow, and that's the flow that basically is the width of the side of the grate or where the flow is entering. Then we have this concept of side flow. There's some flow that doesn't directly hit the front, but will actually come down and go into the side of the grate. And then whatever doesn't go either frontal or side is considered bypass. And that's what's going to pass by this structure. And when we're talking about efficiency, efficiency is going to be basically you know, a factor of how much goes into how much goes past. And just as a sidebar, you know, when we design catchments, we try to have a bypass flow. We target around 10 to 15% to allow it to bypass. If you design to capture all of the frontal and side flow and not allow any bypass, that generally is going to create a lot of catchment structures, and it's not the most economical. So we do allow for bypass. Okay. Now that frontal flow with ODOT methodology, and really with HEC 22, which is FHWA's methodology as well, it's considered 100% capture into the grate. Now the only caveat is once your profile slope of your roadway becomes pretty steep, it's going to increase your velocities. And your velocity, if it gets to a certain speed, it will skip over the grate, and that's called basically a skip over velocity. And you know, in the ODOT methodology, we don't have that built into any of the equations that we currently use. So, you know, we're hopeful that through this research, we'll be able to come up with a methodology to account for that. Basically, once your velocity exceeds that skip over, you'll want to look at another type of catchment, such as a window. Now, side flows, it's an interesting way that we calculate it here in Ohio. And basically we take, here's an image, a cross section of what we're talking about. We've got our grate here. We have a depth out at the edge of the grate, which is closest to the center line of the pavement. We pretend like that's a window. And we just design this like you would any other window inlet. And when you design a window inlet, you take the total Q coming to you, and then you take you do the calculation to figure out what type of length you need to capture all that Q. And of course, that length is usually, you know, quite a bit large. So we back off of that and we say, okay, well, we can't provide that length, but we're providing this length. Let's do a ratio calculation. And that's how we figure out how much Q actually gets into the window. So that's what occurs when we have a graded system. Okay. Now, I want to point out that now we do have a combination system that we're talking about here. We have a grate and we have a window. However, the window is not accounted for any kind of intake on the discharge. That's considered a factor of safety. And that's generally the case when we're on grade. Once we go to a sump condition, that is also the case until your flow becomes significant, you know, using like a larger event, like a 25 or a 50-year event where we really stack up a lot of height on that catchment. Then we'll start to account for the window as well. And you can see through the calculations, the window does a tremendous amount of intake, probably more than the grate, but that is considered a factor of safety. All right, so back to the history lesson here in our grates. What we're looking at over here on the right-hand side are basically the grates and what they look like for a catchment 3A that ODOT uses. It would also be a number 3. A number 3 is just going to be double of these catchments instead of 1. So we did a little digging, looking at historical standard construction drawings, and prior to 1976, ODOT used what we're calling the parallel slotted grate, which is what you're looking at up here. It's the grate L. And this was a great catchment for capturing your discharge. I mean, any reference that you read says that this type of grate is really the most efficient for capturing flow, because the flow is running longitudinally into these grates and it just drops right in. However, in the mid to late 70s, the bicycle safety group came to fruition and really said, hey, this grate is not safe. We need to pick something different. And then in 1976, ODOT introduced this diagonal grate, which was deemed bicycle safe at the time. And there were no changes done to the calculations that we could tell. And we were kind of thinking there should have been some sort of change, because obviously the area of opening has changed here. And that's kind of what made us want to dig in a little bit more and investigate. Vane grates, which you'll see a lot of these today, these were introduced in 1979. Today in our standard drawing, you'll see these vane grates, these V grates, or you'll see these diagonal grates in our standard drawings. And these things down here, they're directional. So you have to put them in the catchment, so at a certain direction, when the flow comes, it hits the vane and drops into the catchment. And they're highly efficient. Your skip over velocity on these type of grates is going to be much higher than this type of grate. Okay, as I alluded to, the parallel flow bars are extremely efficient, and that was highlighted in very old documentation from HEC-12, which was from 1969. And a lot of the equations that we use in the back of CDSS, they were all founded on HEC-12 methodologies. So we did find a piece of research, and we have these standing files at ODOT that contain a wealth of information, and there's stuff in there about historical, you name it. And we went there and we went digging, and we found a paper from 1976 that actually looked at the diagonal grate that ODOT was using, and it looked at the parallel grate, and it compared them with a hydraulic study in a lab. And this was not done for ODOT, it was done for the city of Barberton. And city of Barberton had their own custom grate that they were trying to put on their catchments, and they were comparing it against what ODOT had at the time, which was a diagonal grate and the parallel slotted. Unfortunately, at that time, 1979 is when we put the V grate on, so that wasn't part of this study. And they did show that parallel grates are more efficient than diagonal. And I've got I have a graphic here from that study, and it's kind of hard to see, but this top line here, that's the ODOT parallel grate. You can see it's highly efficient. Here's your efficiency over here. And this is a graphed against the Froud number. And then you have the Ohio.
Hey, Jeff,
yes.
Can we give it a second? I'm going to mute everybody because we're getting some feedback, and then I'll unmute you. Just hang on.
Sure.
Okay, you're unmuted.
Okay, is that better?
I can hear you. Yep, thanks.
Okay, perfect. Okay. All right, so yeah, back to this graph. So this top line is the ODOT parallel, which is more efficient, you can see, than the ODOT directional, which is the diagonal grate, which is this line right here. And consequently, the lower line down here was the Barberton directional, was their custom grate. And you can see the efficiency drops as you change in the grate style. But again, this didn't change any of the methodology that was being used by ODOT in the calculations. So we're kind of thinking we need to look at this in more detail, right? So, some of you may have attended the hydraulic engineering conference in the past couple of years. Argonne Labs, and in particular Marta, has presented on some of the CFD modeling that she has performed with other DOTs. And there's a handful of DOTs that have modeled their catchments or their grates through Argonne Labs through a pooled fund study that's led by FHWA. And they have an agreement with the Department of Energy, which is where Argonne Lab is affiliated with, to do CFD modeling. And it's not just for catchments of grates or inlets, it's for any CFD modeling that we might need, you know, being a DOT. And they have a tremendous amount of computational resources. You know, they have a whole bunch of computing clusters. I'm not real familiar with what they're set up. Marta might be able to dive into a little bit more detail. Then they use a specialized set of software. They have the STAR CCM, they have OpenFOAM that they also use. Okay, and this will be my last slide before I turn it over to Marta. Now, through the pooled fund, we want to look at 4 different catchments, the CB3A, the CB3, the CB6, and then the number 3 barrier inlet. Currently, where we're at with this study, we're pretty early on, and we've just looked at the CB3A. Because the CB3 will be very easy once we look at the 3A because it's basically just double that. But we are doing some CFD modeling. And the beauty of the CFD modeling, it eliminates the need for the full-blown hydraulic modeling, which would either be a scaled model in a lab, or it could be full scale in a lab, and that becomes very expensive. You limit on the different parameters that you can set and change. So CFD modeling takes that into a virtual world and allows you to do a lot more and understand a lot more. So that goes along with our second bullet. We're modeling a variety of different profile grades, shoulder slopes, pavement spreads, different flow conditions, and we're also modeling sump conditions. And with that, I'm going to change it over to Marta and let her take over.
Marta, don't forget to unmute yourself.
I'm muted by the organizer.
Nope, I unmuted you. I could hear
finally.
you. Sorry
That's
about that.
Oh, that's perfectly fine. Okay.
Looks good.
So,
thank you.
Thank you. Hello, everybody. My name is Marta Sitek, and as Jeff already said, I've been working at Oregon National Lab on various projects, but mostly it's different hydraulic engineering problems. And this is a project that I've been working with Dr. Steve Lottes. He was not able to join us today, and so I will present our work to you all. As Jeff mentioned, they asked, Ohio DOT asked us to perform a series of CFD simulations of different flows over the roadway into the, and therefore calculate and establish the efficiency of 4 of their catch basins. And so we usually build a full-scale geometry of whatever we're modeling, because then you can at least avoid those problems or maybe mistakes that could be related to scaling. So in this case, you could see that we have a piece of a road, a section of a road with the travel lanes, with the gutter. We have the V-grade geometry represented here, and also the curb opening. This is one of the geometries. The other 2 that we are considering is with a 4-foot and 8-foot shoulder, and the same with the grade and the curb opening. And the way we model this problem, there are of course many possible approaches. What we decided on is to use Of course, CFD modeling, first of all, the Eulerian approach with two phases, water and air. And for example, on this figure on the top of the slide, you can see the water colored in blue. In the domain, we also have air, of course, which was not represented because then everything would disappear. You wouldn't be able to see the water surface. So Eulerian approach with so-called volume of fluid model to establish where we do have the interface between water and air. And in this model, what we do is at the inlet is on the right side of this model, we introduce a water flow that then can go into the grate, go into the curb, or in some cases also bypass the openings, the inlets. So on the left side, we do have a surface in our domain through which the flow can leave the domain. And we were also asked to take into account a rough surface and asphalt pavement. So in CFD, you have to take this into account as well, and there are different approaches. What we decided on is we will use an approach that we proposed some time ago. We recently published a report on the subject. Because ideally we would recreate the scanned surface of a pavement. That's what you can see here. We would create an STL file which we would then mesh out, but that would be absolutely too big of a problem to solve, computational problem. It wouldn't be efficient. And so the way we model the rough surface is by creating an additional porous region that is impermeable. So the bottom surface here is a wall boundary condition. There is no water going through, but that porous region slows down the flow, and it does not solve for the details of the flow within that rough surface, but it gives us at least a volume average of that effect of the grains of the pavement. And so we had to calculate what would be the thickness of this layer. And by using a Strickler formula from Manning number of 0.015, we were able to establish that this layer should be around 4 millimeters thick. And that's what's added to the model. Just a few results. We are looking at two different conditions. So one is the on-grade location, one is the sag location. So for the on-grade locations, as Jeff mentioned, we are considering different spreads, different longitudinal slopes, and then also different cross-sectional geometries of the roads. And on the left side of the slide, you can see an example. So in this case, an animation for one of the cases that we are running. A top view of the water flowing from the left over the pavement and going through or leaving the domain through the grate and the curb opening here, and also some part of the flow goes out from the domain through the right side of the model, which means that it bypasses the domain, the opening. What we are monitoring during this kind of a simulation. So first of all, we are of course interested in representing the flow correctly. So we monitor the spread, we monitor the velocity of the flow. We of course look also at the efficiency of the grate of the curb opening, total efficiency. We can monitor the flow that's going through the front of the grate, from the side of the grate, whatever is going through the curb opening, and we will be creating those tables of values that Jeff and requested with all of those parameters parameter values. And also we can create some plots which will enable us to analyze all of those results. We are also comparing against the estimates that ODOT is using right now. And for example, here you can see that the efficiency that is a result of our computations is slightly lower than the ODOT estimate, but all of those values are within a few percent from the estimate. When it comes to the SAG locations, this took us slightly longer to set up this model because we were discussing how to set up a CFD model to represent this kind of a situation. And so what we decided on is to create a model that you can see on the left side, a small part of the air and the road around the catch basin. And starting with a pretty deep water above the grate, above the opening, you can imagine that we take away like a piece of a board away from the grate and the opening at the beginning of the simulation, and then the water can flow through those two openings and leave the domain. And this way we created, by monitoring the depth versus the flow rate through the openings, we were able to create the plots that you can see on the right side. They take into account 3 cases. The one that you're looking at on the left side, which is a combination of the grate and the curb opening, and also a case in which the curb opening is blocked, let's say by debris, and the other case where only the grate is blocked and the curb opening is open. So the solid lines are CFD calculation or results, and then the dash dot kind of lines, these are the estimates from ODOT. And you can see that in 2 cases, the ODOT estimates, they are more conservative than our results. And in the case of the curb opening inlet open, the 2 lines almost overlap. And so the results of this study, this is an ongoing study, that's why I'm showing only a few results, and kind of more, I wanted to focus on talking in general about the modeling approaches and what kind of results we will be getting at the end. We will have overall about 90 on-grade test cases. We have those 3 sub-conditions that we were talking about, that I was talking about, and we will be post-processing, of course, all of those results and analyzing them to find the relationships between different types of flow, efficiency, and also we will be looking at the comparisons between our CFD results and the ODOT and also HEC-22 estimates. And this would be it from my side. Thank you for the opportunity, and if there are any questions, I will be happy to answer them. Thank you.
Okay, thank you. We do have just one question. I think this is more for Jeff. Is there going to be a future update to ODOT CDSS due to these research developments?
Love that question. Yeah, so how much time do I have, Becky? Just kidding.
1 minute.
No, I mean, yeah, there will be some updates to CDSS. We did have some funding. We were going to move forward with it, and then COVID hit and our funding got dropped. So we will be going full circle, trying to acquire some funding, and maybe that's a good thing, so we can try to take some of these results and refine them before we incorporate them. Good question.
Okay, that was the only question, so we can move on to the next portion of this. I'll introduce Kevin White next. Kevin White is the Water Resources Manager with E.L. Robinson Engineering in Columbus, Ohio. He has 29 years of experience in hydraulics, hydrology, water quality, and the structural mechanics of buried pipelines. He will graduate with his PhD in civil engineering from Ohio University in December, having recently defended his dissertation. This presentation is a brief overview of his dissertation research concerning rerounding of deflected thermoplastic conduit. Kevin?
Thank you. Can you hear me okay?
Yes.
Great. So as Becky said, we'll be talking about rerounding of deflected thermoplastic pipes, which was my dissertation for my PhD. A necessary disclaimer, my dissertation was a very, very small subset of a larger project, and so it's an ongoing work. So want to make sure that everybody realizes that the research isn't done yet. ODOT's not reviewed the work in its entirety. So nothing in here should be construed as a standard or as an approved ODOT research result. So we'll talk about today, we're in quick introduction, what I'm talking about. We'll go through some field experiments that were run, talk about some results and analyses, some of the finite elements that we went through, and some quick conclusions. In the field experiments, we actually have a whole slew of instrumentation, measurements that were taken, and I could probably talk for the better part of 2 hours to try and cover all of it. But today we're just going to talk very quickly about the pipe shape, the pressure cells, the accelerometers, and a little bit about the finite element analyses that we went through. So thermoplastics are pretty common at this point for runoff conveyance. HDPE is probably the most frequently used for stormwater. Despite us really knowing that when you install the pipes well, they perform very well, but we continue to see poor performance in the field. Typically, we see excessive deflection. When we talk about vertical deflection, we're basically just meaning the change in the vertical dimension of the pipe as a percentage. So AASHTO section 30 tells us that if the deflection is greater than 7.5%, the pipe should be remediated or replaced. ODOT has a similar criteria and says that it's over 7.5, you have to remediate it or replace it. The method of remediation is left to the registered engineer, who is the one who's actually doing the inspection of the conduit. So there's kind of a gray area in terms of what we do to try and remediate the pipe. Rerounding is a very, very common method of rerounding thermoplastic pipes with their over 7.5% limit that AASHTO or ODOT tells us that we have to. If the pipe isn't really experiencing any other forms of defect, buckling, cracking, anything like that, rerounding is a viable option. And what really happens is it's a combination of vibration and internal pressure. So if you look at the picture, you can see that that upper portion of the rerounding device actually is hydraulically actuated upward, and it's actually pushed against the crown of the pipe while that whole apparatus is vibrating. And those two processes mobilize the backfill material and allow the pipe to be rerounded. Now, despite the fact that this particular product has been around for the better part of 30 years, there's actually been no detailed research on what's the mechanistic impact of this rerounding to the pipe and the backfill. So that's what we were trying to take care of. So we did a series of field experiments, 3 in total. And what we did was we varied the backfill and we varied the target deflection. What I mean by the target deflection is when at the installation, we purposefully installed these pipes poorly with the idea that we would target either 10% or 15% deflection when the pipe was installed. And interestingly, we really struggled at times to get the pipes to deflect. So I have to be honest, I'm not sure how this is necessarily happening in the field because we really had a hard time getting some of these pipes to deflect. The layout is pretty simple. We have 3 sticks of pipe, 10, 20, and 10. This way we can capture the joint performance. And for all of the testing, they were 36-inch diameter pipes. Cross section of the installation, it's a trench, partial trench installation. So the 6-foot a backfill above the top of the pipe, 3-foot pipes are about 10 feet in the ground. Put another 4 feet on top of that for a total of about 10 feet of fill. 6-inch bedding beneath it, which is what ODOT requires or used to require in the CMS, and which is fairly typical for installing pipe. 3 backfills, the 3 different ODOT backfill materials, type 1, 2, 3. One is basically number 304 road base, well graded, everything from sand all the way up to about a number 57 stone. Type 2 is a sand, and type 3 is actually a 57 or 67 open graded aggregate. The instrumentation included pressure cells. We had pressure cells in the crown and in the spring line. They were located 7 inches radially beyond each of those 2. Accelerometers were installed, both horizontal and vertical. 2 different sets. One set at 6 inches above the crown, the other at 12 inches above the crown. The reason for the accelerometers were to understand the vibration of the rerounder and what type of soil accelerations we were seeing, and to understand if those soil accelerations could actually be damaging to the pipe, or I'm sorry, to the pavement above the pipe. And later on, I'll kind of show you how we went about those calculations. We also directly measured the inside diameter of the pipe at 10 test locations shown in the figure A through J. This was a stepwise procedure, and it was done via a laser profilometer that was designed by Ohio University. So if we look at the results, test pipe 1, we have the results as representative results at section E. Our vertical deflection was about 10 3/4% before rerounding. It was about 7.5 after rerounding. In the spring line on the right side, you can see that there's some signal noise in there before rerounding. So that leads to some complications in trying to understand what's going on. But we have enough good cross sections that the signal noise wasn't that, it didn't impede us that much. But what you see is the cyan line is the before reround, the initial. The red is before rerounding, and the sort of golden is after rerounding. So you can see the change in the pipe during the 3 different test measurements. This is a lot of information. It's just basically a summary of test pipe 1 shape data. Vertical deflections was really important in this, is the vertical deflections before and after, and the delta before versus after. And if you go to the far column for the vertical deflection, the delta after versus before, you can see that we were improved by about, roughly 3%, 3-4%. And summary of those data is that before deflection, we had about 10 3/4 to about just short of 14% deflection. Pardon me. We after rerounding, we varied from about 7 to about 8.5. So a fair amount of reduction in our overall vertical deflection. Similar for test pipe 2. At this location, there was too much signal noise, and so we couldn't actually take measurements at cross-section E, so I went to cross-section D. And before rerounding, we had about 7.3 vertical deflection. After, we dropped down to just about 6. Again, we have a summary of our data, and so what we see is, again, going over to the far column, the delta before and after. In this case, we improved by about 1.5%. Not quite as much as what we saw in test pipe 1. And as a summary, we varied from about 6 to 9.5, not just short of 10. And after, we got down to about 4.5 to about 8.5. Again, the performance of the sand wasn't quite as good as the performance of the 304 in terms of the ability to reround the pipe. And lastly, we look at test pipe 3, which, if we recall, was the number 57s. In this location, pardon me, we looked at cross-section F. Again, cross-section E had some difficulty with some signal noise. Before rerounding, we're at about 10%. After, we went all the way down to 2.5%, a dramatic reduction in vertical deflection. And again, if you look across the board, if you look at your delta, the last column, you see these tremendous numbers. Thing to keep in mind is that this was after one pass of the rerounder. So basically, to just go back and summarize, with the 304, we actually made 3 passes of the rerounder. Test pipe 2, we used 2 passes of the rerounder, and test pipe 3, we used 1 pass. And on test pipe 3, we see tremendous reductions in the vertical deflection with a single pass of rerounder. And the summary, we varied from 4 to 10, and afterwards we went down to 0.6 to about 2.5. So a fairly substantial reduction in vertical deflection. What do we get from all of these analyses on shape? Backfill 3 was by far the most amenable to rerounding. And honestly, that should be expected because it has the highest void ratio, and the particles are able to mobilize themselves easiestly under vibration. We saw about 7% deflection removal with a single pass of rerounder. Type 1 and type 2, much lower void ratio, so it shouldn't be a surprise that these were much more difficult to reround. Of the type 1, we had an average about 1% of deflection per pass of the rerounder. And type 2, we had about a half, a third, 2/3 of a percent removal with each pass of the rerounder. Next, we'll look at some of the accelerometer data. So on the far left, you see the actual accelerometer data that's coming directly from the accelerometers. So the first thing we have to do is we have to change this data to a frequency response. So we do a past Fourier transform. And from the past Fourier transform, we can determine the dominant frequency. In this case, the dominant frequency was 48 Hertz. And I'll explain why this is important in the next slide. But what's important is that the dominant frequency was 48 Hertz. So we look at the accelerometer data. Once we know that frequency, we can actually go in and we can change accelerations into velocities, and that's what we're trying to accomplish. So we take these peak vertical accelerations using the equation that you see in the middle of the screen. We're able to change these into peak particle velocities, and then from these particle velocities, we're able to calculate what's called the damping coefficient. What's interesting is now that we have the peak particle velocities, we can actually use one of the accelerometer data sets that we know. We can plug in assume a maximum limiting peak particle value velocity for like a pavement or something like that. In this case, there's really no good data. So what I did was I used 1 inch per second, and that is actually the value of a masonry wall, underground masonry wall. And it's a guess. I can't say anything other than that, but it's a guess. So what we do is if we then go in, we can calculate what's the distance to get to that 1 inch per second peak particle velocity. We go through this calculation, we get 50 inches. So what's that telling us? That's telling us that at 50 inches, we'll get 1 inch per second as a peak particle velocity. If we say that's where we are at incipient damage of damaging an asphalt pavement, we can set the minimum depth of 50 inches and say, you know, if we have 50 inches, rerounding is viable. Test pipe 3, we did something similar, and what you should expect to happen happens, which is that since these particles are able to move more rapidly or easily because of the high void ratio, we actually end up with a much more damping, and since we have a lot more damping, we actually end up with only 6 inches is all you need to make sure that you wouldn't damage the pavement. So basically saying that it's almost impossible to damage the asphalt pavement with the type 3 backfill during this rerounding process. Next thing we'll look at is we'll look at the backfill. And what you're looking at here is you're looking at test pipe 1. We took samples of the soil before rerounding. We then took targeted samples after the rerounding at the crown at the spring line. And if you look at the gradation of the material, the cyan is before, the golden is at the spring line after, and the red is at the crown after. And what you can see is you can see a definite change in the material gradation. And what you're seeing is you're actually seeing fines moving out of the material. So you're seeing a material that after rerounding has less fines, which is an indicator that the vibration basically results in fine particles in the soil moving from upper levels to lower levels. And another way we can test this, if we will, like numbers, and engineers like numbers. So what we look at is we look at the coefficient of uniformity, coefficient of curvature, two different ways to determine what type of a material you have, whether it's well graded or poorly graded. Well, if we look at the coefficient of uniformity, that would tell us that it's well graded before and after. But if we go through the coefficient of curvature, we'll see that it says it's well graded before, but it's poorly graded after. So again, this is just an indicator that the material constituency is changing because of rerounding. Considering also the soil, and we look at the pressures. We look at test pipe 1. Keep in mind that geostatic in this particular instance is about 8.3 psi, assuming 120 psi soil. If you look at the pressures, in all cases, we see a significant drop in the pressures. Now, when you're talking about 30 days before to immediately before, we see a small drop, and that's really the stress relaxation in the system. But then when we look at the actual rerounding process, pass 1, pass 2, pass 3 for that particular day, they all occur on the same day. The rerounding process also results in a significant drop in soil pressures at the crown and spring line of the pipe. Exact same results for test pipe 2 in terms of the trends. The numbers are different, but the trend is exactly the same. A significant drop in pressures around the outside of the pipe. Test pipe 3 was a little bit funky. It didn't follow the same trend. And the reason I believe that this happened is I believe that the sand, we usually put a sand layer around the pressure cells to help normalize the pressure being applied by the 57s. And I'm guessing in this case that the 57s were just making too good a contact and we're getting point loading. And that point loading tends to decrease the overall pressure in the pressure cell. So what do we say? We say, wow, test pipe 1, we saw a crown pressure reduction of 88%, 91% for test pipe 2. We see a 53 and 68% reduction in soil pressure at test pipe 1 and 2. And as I talked about, test pipe 3 does not follow the same trend. We saw an increase in pressure at the right spring line and crown, but we saw a decrease in pressure at the left spring line. Last thing I'll talk about is some of the finite element work that we did. We used program MIDAS GTSNX. The reason we used it, it's a geotechnical specific FEA code. We used a plane strain approximation. You'll consider plane strain if you look at your system and you say that every system longitudinally or every cross section longitudinally is the same, then plane strain is appropriate. In this case, we felt it was. The pipe was modeled as 2-node beam elements. The soil was modeled as 3- and 4-node continuum elements. The model had 660 elements, 665 nodes. Compared to what our last speakers were talking about, this is child's play compared to what they're doing. Look at the model. You see our bedding, all the different soil zones that we utilized, the bedding, the in situ material, backfill, and embankment, all different material models utilized. The beam is used a 30-day modulus of HDPE of 60 KSI. The structural backfill and bedding were Duncan Chang hyperbolic elastic plastic material models. Everything else was linearly elastic. It was a static analysis, and the obvious question is, this is such a dynamic process, why did we choose static? Well, the reason we use static is because the Duncan Chang is an elastic plastic model, and if you don't approach the plastic limit of the material, then it's purely elastic, in which case static and dynamic makes no difference. And actually, one of the first runs I did was a dynamic analysis, and you saw that there was very, very little difference between them. Did a total of 9 different analysis cases of 3 different compaction pressures and 3 different rerounding pressures. And the reason we did this is because we really didn't know what was the rerounding pressure, and we really didn't know what the compaction pressure was. And so I just looked through literature, found out what common compaction equipment produces in terms of pressures, and then I utilized the exact same 3 numbers for the rerounding because it seemed like the energy was similar between the two. We used construction increments. You can see the different 8 different construction increments that we utilized in terms of trying to build the model. And our results, when we look at the vertical deflection before we reround, the FEA tends to under predict the vertical deflection. And this is really fairly common in FEA unless you get into some very, very advanced soil models. It's very, very common to see this type of a result. Now, what we didn't really know what was going to happen is on the rerounding after we reround it. And what we see after rerounding is that it tends to overpredict the benefit of rerounding. And part of that is because of the fact that it tends to underpredict the deflection. If we look at the results just from a graphic standpoint and we look at the soil pressures, and what I'm pointing out here is the actual, that element is the element that's 7 inches above the crown of the pipe, which is where the pressure cell was located. What's interesting is we do see the same trend in pressures, though. We see a drop from about 6 psi down to about 3 psi before rerounding and after rerounding. Similar at the spring line, we see a decrease from about 7 3/4 or 7 2/3 down to about 6 psi. So when we look at a table and what we do is we're just kind of trying to understand how does the FEA result with what we actually saw in the field in terms of soil pressures, radial soil pressures. So what I did was I took a ratio of the test pipe value, the field value, versus what the FEA gave us. So if you're looking before rerounding, the results are actually fairly good. You know, a ratio of 1.01, that means we're only 1% away between the two. And even if you look at the worst case, we're at 1.44, so we're 44% over predicted. But that's not terrible when you're talking about dealing with soils and you're talking about dealing with trying to utilize soil models that may or may not be terribly effective indicators of actually what happens in the field. Now, after rerounding, that's when things kind of fall apart, and you see that very poor performance. What we can say is we can say that it's relatively successful in predicting shapes and pressures. I don't know that I would go any further than that. And really, that's it. That wraps it up. If there's any questions, I'm happy to try and answer them. And otherwise, I thank you for your time.
Thanks, Kevin. We do have several questions. We'll start off with this one. How is the pipe rerounded? How does the rerounder machine work? Maybe if you could explain that a little bit.
Yeah, so what happens is there's an eccentric vibrator in the rerounding machine, and the rerounding machine is actually almost like 2 different halves, 2 different semicircles. And what happens is the whole apparatus vibrates, but then those 2 halves kind of separate apart, and those 2 halves kind of push up and down onto the crown of the pipe and the invert of the pipe, and while they're vibrating.
Okay. Next, does rerounding damage the corrugation's pipe structure?
Well, that was one of the things that I didn't have time to talk about, unfortunately. But the overall consensus from the 3 tests that we've done so far is it doesn't appear to be. There does not appear to be any damage to the corrugation. There's a slight reduction in overall crown in the corrugation height after rerounding, but by no means is it enough to be above the strain limit of the polyethylene.
Okay. Next, how do you prevent the pipe from going back to its deformed shape since the backfill keep placing the same pressure and stress on the pipe?
Well, it doesn't. If you looked at, if you go back to my you go back to my slide where we looked at the pressures around the pipe, there's a significant reduction in the pressure around the pipe. So there's a relaxation that's taken place because of this. So there are pipes that have been in the ground for 10, 15, 20 years that have been rerounded and have not returned. And part of the reason is because, again, this was not, we looked at it, but I didn't present it today just because of a lack of time. But we also looked at the stiffness of the soil. And what we see is we see a much more uniformity to the soil stiffness around the entire periphery of the pipe after rerounding when compared to before rerounding. And so that uniformity to it puts you in a situation where you're much more likely to be in a relaxation mode as opposed to a creep mode.
Okay. Let's see. What compactive efforts were performed during construction of your test pipe 3 with number 57 stone as initial backfill? Were any density tests taken?
Well, you can't take density of a 57, but to answer the question, none. There was no compactive effort at all placed on the 57. In fact, we had to deflect the pipe ourselves because we were not able to get the pipe to deflect. So that we're seeing deflection in the field with 57s and polyethylene, I don't know how it's happening, because we used sheep's foots, we used hoe rams, we used everything we could think of to try and get the pipe to deflect, and we could not get it to deflect. We actually ended up having to deflect the pipe with an apparatus, place the material above it, and then it was all end dumped until we got above the top of the pipe, and then we started vibrating it.
Okay. Let's see the next one. Did you check if the rerounding rebounded to original deflection after 30 and 60 days?
We did look at it, and there's very, very little movement. There's almost no recovery at all. I mean, the pipes are essentially unchanged after 30 days, and actually some of the pipes were in the ground for over 80 days. And so there was no change in shape, essentially.
Okay. So do you have any, this one said, it might be just a little bit more on that last question. How does the pipe perform 5 years after rerounding? Does it deflect again?
I can't say specifically because this is only a 1 year. You know, these test pipes are left in the ground for the most, I thought, about 80 days afterwards. But there's literature. There are some studies that some manufacturers did where there was a stick of pipe that was rerounded up in Cleveland, and they came back 10 years later, and the shape is essentially unchanged.
Okay. Are there any potential recommendations to CMS?
I will defer to ODOT on that.
Let's see. Were impacts of construction trench widths studied relative to backfill type?
The trench width was constant for all the tests. There was no variation in trench width.
Okay. How did rerounding affect the roadway above?
There was no roadway above it in the testing, which is part of the reason that we use the accelerometers. There is some anecdotal evidence that it could impact the pavement. Honestly, I would be more concerned about when you're vibrating it, that you're getting some consolidation of your material, and so you're getting the trench to sort of move down. And so I'd actually be more worried about the pavement distress coming from that than from what the rerounder is actually causing through soil accelerations.
Okay, yeah, and that kind of goes to this other question. On top of that, would scour be a larger concern for any of these rerounded pipes?
I don't understand the question, scour.
He says, are there any concerns that by rerounding a pipe, the surrounding soil compaction is reduced, like you were just talking?
No,
And
it's
would
actually,
scour be a larger concern?
the compaction is actually increased around the pipe. We see a densification of the material, particularly in the haunch, where the haunch is usually very, very soft. So there's a really, really slight reduction in the stiffness of the soil at the crown and at the shoulder spring line.
Mhm.
But in the haunch, we see a huge stiffening of the material, and it just ends up being a much more uniform presentation. I think we ought to stop there, Becky.
Yep, that's good. We will get these other questions answered by email.
Thank you for your time. I appreciate it.
All right. And the next presenters are James Castle and Luke Darby. James Castle is the Assistant District Manager with EJ, formerly known as East Jordan Iron Works. Mr. Castle has a degree in civil engineering from Lawrence Technological University in Southfield, Michigan. He's a lifelong Metro Detroit resident with 22 years of experience in the industry, including the last 5.5 years with EJ. Luke Darby is the Columbus office branch manager and technical sales specialist for EJ, covering Ohio, Kentucky, and West Virginia. With over 12 years in the construction industry, Luke helps cities and engineers to develop solutions for their infrastructure needs. Luke has earned the OSHA 30-hour safety certification and holds a BS degree in construction management from Brigham Young University, Idaho. James and Luke will be discussing innovative access solutions. All right, go ahead, Luke.
Wonderful, thank you. It's a pleasure to be here today and to have the opportunity, first of all, to listen to some other great presentations, and then also share some of the things as a company that we've really found to be helpful. As a company, EJ, we've been in business since 1883, and we are a family-owned business based out of northern Michigan, and it's something that, you know, in the past 137 years, especially, there's been a lot of changes to the casting industry. The photos and the pictures I have here now show some of our early days, and then some of our more recent different processes and facilities and such that we have. So as things have changed, especially in the last 10 to 20 years, I'm going to focus a lot on the product changes, on some of the newer to market products that we're offering that really were born from a need. That these products are a result of conversations that we've had on job sites with, you know, municipal superintendents, with field workers, conversations that we've had in many engineers' offices throughout Ohio. And what this has done is it's been an opportunity to bring those that are seeing some concerns and issues in the field, those that are seeing, hey, you know, if you made this a little bit differently, or have you thought of doing this? And it's really given us an opportunity to get in the field, to be with, you know, those that are installing and utilizing a lot of these products. And then also, again, the design side with many of you, to look at improving things like performance, improving safety, and then just, you know, addressing and hopefully solving problems that are certainly out there in the field for many of us. So what I want to share with you right now, the first product I want to share with you, this is a composite rubber adjusting ring. We have met with a lot of municipalities and cities, and I would say, barring very, very few, most municipalities have significant issues and struggles trying to maintain and control infiltration. A lot of times you'll see around the top of a manhole frame that's in the street, you'll see a lot of breaking up of the asphalt or the concrete around the frame. And what this composite rubber adjusting ring is designed to do is it actually acts as a non-rigid connection between the underside of the manhole frame and the top of the structure, whether that structure be concrete, whether it be brick. That rubber adjusting ring acts as that non-rigid connection. A lot of times we get asked, you know, are these designed to replace concrete, you know, concrete grade rings? And the answer to that is no. There's many municipalities in Ohio that are currently using and use heavily these rubber adjustment rings for that final grade adjustment, whether that final grade adjustment's 1.5 inches, 2 inches, 3 inches, whatever it may be, or even down to 1/2 inch. These rubber adjustment rings allow for that, that first of all, that good, hard, tight seal between the underside of the frame and the structure, but also, again, that non-rigid connection. They're extremely easy to install. You know, it's really a one-person job. These are made here in Ohio from recycled materials. So if you're designing a job that needs LEED rating and certifications, these are 97% recycled material, recycled tires. And the only thing that part of this is not recycled is just the binding agent that we use to make these. It also does mitigate some traffic vibration concerns and issues. And this next slide, what I hope that this slide, this graphic will illustrate is that as a car or a vehicle is traversing over top of the frame and cover, it's transferring that load. And normally, under normal conditions where that final grade elevation was made using, for example, a slurry of mortar, maybe a row of brick. We've seen all different types of things used to shim the underside of a manhole frame. None of those products help disperse the load, whereas rubber disperses the load. First of all, the arrows that are pointing kind of east and west, and then a little bit of the southeastern or southwestern direction, those are indicative of that rubber helping to deflect that load out to the subsoil and the subbase, which in turn helps take a lot of that load off of the top of that structure. Because as that iron beats on that structure without an inferizer in there, or without a rubber adjustment ring in there, what it does is that if there's any imperfections in either that mortar bed or the brick or the concrete, that iron's going to win. And over time, that structure will degrade, fall apart. You start losing your fines, and then you start having tremendous issues with infiltration. So as municipalities, your customers are paying to treat water that they shouldn't be paying to treat, in addition to the road surface really breaking up and having tremendous issues in and around the structures that are out in the roadways. So that's this illustration. I just want you to help guide you in that thinking and understanding that this is not compressing that rubber adjustment ring. That rubber adjustment ring is traffic rated. It has very, very similar properties, compressive properties of asphalt. We don't want it to have a memory, because if it's moving and compressing and squeezing, then so is everything above it. So is your asphalt, so is your subbase, your road base, all that's moving. And we want to restrict that movement to allow those forces to be really dispersed out into the soil. One of the great things about these rubber adjustment rings is that they come in thicknesses all the way down to a 1/2 inch, all the way up to 3 inches in thickness. They are made to fit really all of the castings that we make. We make an inferizer that can be utilized in that capacity, whether it be a manhole, a catch basin, a curb inlet. If you have some really, really old castings and unique situations, we even are able to cut strips and send those out. There's several municipalities in and around the Cincinnati and Dayton areas that I work with heavily that use their own custom ones. We also offer these as a tapered application. So we recognize that not every road is flat. A lot of them have a pitch to them, and we can actually taper these up to 2 inches in difference. So if one side of it is at a 1/2 inch, the other side we can go all the way up to 2.5 inches. So it allows for that tapering as well. It's a wonderful product that really helps meet those needs. And helps really minimize, if not eliminate, infiltration concerns. This is my favorite casting, and this is going to be something that may shock a lot of you. I love castings, but this casting in particular, this pivoting casting, is to be used really in applications where you have a raised structure. What this does is it helps minimize and eliminate shoulder injuries, back injuries, issues where you have a cover coming off the top of a structure, either going down and falling down below and hurting stuff down there, or, which I've seen a lot, is especially areas around riverbeds that you don't have. There's not even covers on the top of the structures, because no one's going to carry it back up a ladder, a 200 or 300 pound cover, to set back in place. So these are designed for use in elevated structures where that cover actually rotates on that pin. Rotates on that steel pin or stainless steel pin, and what that does is it allows that you don't even have to remove the cover in order to gain access. If you're going to do something like pulling inverts, shooting inverts, you don't have to remove that cover and carry it up and down a ladder anymore. It's a quarter, just a very slight lifting, and it'll rotate in either direction. We do offer these as watertight. In watertight applications, they will be bolted down, like the one in the top right corner shows 4 bolt holes there. That frame and cover are bolted together for watertight applications. These are not traffic rated, but they're not designed to be put in traffic areas. They're up on raised structures to allow for really just a safer way of doing business and safer for those in the field. This casting here, it's called a storm surge casting. What this does is it allows for areas that have concerns of flash flooding or tidal concerns. It allows for that system to burp. So what happens is that head pressure builds up, and that cover normally would just float away during a high water incident. That cover actually underneath it, you see in this graphic here, it has a little a catch on it. And what that does is that locking arm and hinge, the locking arm, as the pressure builds, that cover opens up, catches on the other side of that, allowing the system to burp and then rest back in place. That arm can be removed so that you can have full access to the vault. One of the considerations that we need to take into account when designing these is that you don't want to build traffic stops into the road. So there's a direction of open on these, a direction of flow, and just making sure that if it's in a roadway, it allows that we allow for it to properly open in the right direction. I'm going to share a video real quick here. What this video is going to show is that pressure build, casting cover lifts up, engages with arm engages for the system to burp, and then flows down as the So a lot of these applications allow for us really to, this one in particular, just allows for a safer and cleaner work environment. Another
Luke, we
product
need you to reshare your screen, please.
All right.
Thank you. It's through the drop down. There you go.
All right.
Thanks.
There we go. All right. So the next product I want to briefly mention to you is are your aluminum hatches. So aluminum hatches, we meet with a lot of municipalities that have extremely aging infrastructure. And aluminum hatches are one of those kind of target areas for a lot of municipalities. I want to draw your attention real quick to the bottom three pictures here. This is a top mount aluminum hatch. A lot of times we will have applications like this in a lift station or pump station where the old hatch over time has failed. What we'll do is we'll go in and measure the clear open and then design a hatch that sits up over top of it. So all they have to do is remove the door of the old hatch, put a little butyl strip down and place this hatch back in place. And then just bolting it down. There's no concrete top work to be done. And it also allows for, as you see there, an orange safety grading mechanism there that allows for all the visual inspections, float adjustments to be done in a safe environment where there's no risk of falling. Recognize that not every application, that aluminum will not work for every application where it's going to see traffic and regular traffic, which is why we have a ductile iron version of hatches as well that allow for all the way up to be used in airports, meeting or exceeding a 200,000 pound proof load rating. These get very heavy, but thankfully there is a lift assist that one person can operate these. It's about 35 pounds of lifting force is all that's needed to fully open and fully close. You get that assist all the way down. Again, we have some hinge castings that allow for easy access and and much safer access to the vaults, especially things that you're having to access on a regular basis, whether they be manholes like this, or the other ones here, different hinged inlets. We also have larger clear open ones for example, utilities and different communication vaults and such. The hinged inlets are wonderful because anyone who's had to fish a grate out of the bottom of a structure knows that it's an almost impossible task. These hinged inlets really keep that from happening. Last product I want to go over real quickly is the composite casting. Our composites really provide improved ergonomics. They are telemetry friendly, so you're not having signal interference like you do at times with iron. There's no scrap value, so in areas of really high theft. We have a lot of municipalities around the state that really utilize these different products. So if you have questions or want some references to customers that we've worked with around the state on any of these products today, please feel free to ask. I'm going to turn the time over now to James Castle.
Good morning, everybody. I hope that everyone can see my screen just fine. I did draw the short straw, the last 15 minutes of a 90-minute presentation. So I'm going to try to keep it moving along, but I do want everyone's attention. I want everyone to maybe close that solitaire game and go ahead and take a look up at the screen and strap in and get ready. I'm going to expand a little bit upon what Luke talked about, but from a little bit more of the design side. You know, the title of the presentation is the evolution of the casting. It should be the evolution of the solution. And we're going to touch on a couple of items, really from the design aspect, but where do we go from here? I'm going to challenge all of you to be a little bit daring. You know, not white after Labor Day daring, but just a little daring. I want you to take one step forward. I mean, the audience today, obviously I can't see you. I'm not certain who's there, but I can tell you almost 500 people involved in the industry that we are in, whether it be design, construction, management, industry representatives, manufacturers. We all have a responsibility to take a step forward. Now, I'm not going to pick on Jeff. But he did note in his presentation earlier that the casting change was done in 1976. And so there's been changes since 1976. I'm not saying that standard is 46 years old, but there's been a lot of improvements in that time frame, and particularly in the last 10 to 20 years, like Luke touched on. So I kind of wanted to take a look at the performance side of a casting and the weight side of the casting. Currently, a lot of the standards are based solely on weight. Well, why was that? Why is that still to this day? Because weight was a measurement back many, many years ago, particularly when the class of iron wasn't the standard class 35B. Now, Ohio has adopted, and ODOT it follows the standards of AASHTO M306, which does mandate class 35B iron. Okay, back when weight was really the way to go, that grade of iron was much less. Why? We couldn't test it. We didn't have the capabilities. We didn't have the modeling. We didn't have the computer software. You know, we talked about finite element analysis in the last presentation. That is all available to us now. So the theory always was that heavier is inherently stronger, right? Why? Well, I'm going to show you in a couple slides that that's really not the case. But inspectors used to test the weight of the castings on a scale on a job site many, many decades ago. And so that was why weight was part of the standard. Now, and again, not to focus on just the ODOT standards, there is some language in there that does say if you have a lighter casting, but it meets certain standards, it can be evaluated. That's a great step in the right direction as a group. Okay, as a group, that's a great step in the right direction. Okay, so it's kind of a love-hate relationship with castings. I want it heavy, but I don't want to have to lift it. Okay, so where to go now? Well, let the experts be the experts. I mean, I was intrigued by Jeff and Marta's presentation when they were talking about modeling the flow and how they evaluate it. That's a great starting point for, as an industry, us to gather with the designers and come up with a possible better solution. I've seen it, and I've seen the modeling that we do as in the industry. Just chamfering the edge on a grate changes the flow dynamics dramatically. Something that you wouldn't even think about could change it. A sinusoidal grate as opposed to a straight grate to allow for the different flow. Again, my challenge is to continue as a group to have these conversations, to rely on each other, but come up with a better product or a different product for different applications. Okay, we have the tools, we have the capabilities to do that. I mean, back when weight-based standards were prevalent, you know, ergonomics was not really a factor. Well, it is now. Why? Because of lawsuits, because of safety and working conditions. Okay, so again, along that line, not just looking at going to a performance-based standard from a weight, incorporating the two together, finding the happy medium, but the evolution of materials as well. Ductile iron has a number of applications where it can be incredibly beneficial to use in lieu of cast iron or in conjunction with cast iron. Okay, that really, the use of ductile iron has really expanded the repertoire of the industry as a whole. Okay, again, several of those products that Luke showed you had ductile iron in them. Let the experts be the experts, but work in harmony, work in conjunction with one another. I mean, from a modeling standpoint, cast iron is very difficult to model. Why? Because when you test it, it fails, and that's it. It fractures, it's done. When you model ductile iron, it yields, but then it has to be taken another step to fully fail. So we could take all of what we've learned and take all of what you've learned and come up with a better solution. I mean, again, Luke mentioned it. Do you think those products came up just from designers being creative, sitting in a room behind a computer? No, they came from collaborations between industry professionals, just like the people that are on this virtual conference. All right, that's where that came from. There's the ingenuity and the collaboration will come up with a great solution. Okay, now does it mean change everything? No, it doesn't. You know, again, all that valuable research that we saw earlier really is important for all of us to have. All right, so I'm gonna jump through. Again, that's the platform. I want to take a look at the process. I want to take a look at the standard, and I want to take a look at the materials. Okay, so we're going to move through here. I'm going to touch on a little bit of technical information. Let's see, are we moving forward here? There we go. So I touched on this. This can be found in the standards for ODOT, and I'm sure that for designers out there, you include these standards in section 1 of your specifications. But this is the ASTM A48 is the standard for cast iron or gray iron. A536 is the standard spec for ductile iron castings. Okay. And then we'll talk a little bit about AASHTO. AASHTO M105 and M306. Really, it's 306 that is the driving force. I mean, these two as an industry, ASTM and AASHTO, really dictate how us as an industry provide our products. And again, the adoption of these standards is a big part of the specifications that go into Ohio. And again, AASHTO references the materials, the class 35B, the ductile iron, the proof loading, right? The tolerances, inspection and record keeping, certs, markings, and records. So I mentioned a little bit about the difference between cast and ductile iron. From a molecular level, it is different. Cast iron is more flaky, and ductile iron is more spherical. Okay, now basically cast iron is inoculated with a bunch of admixtures, but magnesium is the primary admixture that goes in there, and it does change the makeup of the iron and provide ductile. So that's one piece of that. Just the understanding, do your research on ductile. Allow us to provide, as an industry, provide research on ductile and its benefits. Ask the questions. Okay? It's hard to build a house if you only have half the tools. Ask the question. Okay? So I mentioned earlier about heavier isn't always stronger. That was the theory for years. Here's a platen cover on the left, a rib cover on the right. Ribbed is an old school way of designing and building and manufacturing casting. Has been for years. Will continue as an industry to make it because there'll be a demand. Platen cover is more of an evolution that really was developed through finite element analysis. But all that aside, case in point, let's talk about heavier not being stronger. Here's a 245-pound cover, 28 3/4 inch diameter, class 35B gray iron. Here's the test. Fails at 63,000 pounds. Meets H20, meets H25 loading. Okay. Same cover with platen design. See, the bottom here is different. 28 3/4 inch, class 35B iron, 165 pounds. By my math, that's 80 pounds lighter. And this one fails at 103,000 pounds. 80 pounds lighter, 40,000 pounds stronger. Why? Because we looked at a new way of doing it. We looked at a new way of building it. And the industry has adopted this throughout a lot of different product lines. We took a step. With the help of modeling and then going forward with testing, we took that step. The same step I'm asking all of you to take. So where does that lead? That leads into products like this where there's a mixture. This is a hinged casting that Luke discussed. It's got a ductile iron cover and a gray iron frame. This was designed for performance. It was designed to meet all these different requirements. So if you're wondering where to start with this, where to start learning, where to start knowing more about what's out there and available to you, there's websites. I'm particularly impartial to one, but there are websites out there for people to be able to access this information. Okay, that's where to start. Got to find that first step. There's also, for designers, there's also multiple locations to be able to find certain standards and specifications. Again, going back to Dr. Sitek and Jeff's, their presentation, there's calculators that are available. Well, I wonder if that casting is going to work. Well, how do I find out? Well, here's a way to find out. There's websites out there that have drainage grate flow calculators. And what's great about them is they don't stop there. They push you to the next step. They help you find the right solution. Also along the lines of cast iron detectable warning plates. And they also, that's there. I don't know about you, I didn't always do real well in geometry. And so this has been a welcome tool to have, but there are resources out there for you. Okay, there are resources out there for you. This is a great place to get started. You can also talk to us. We're happy to help. I don't know if you can tell or not, but Luke and I are very passionate about what we do. We are here to help. We want to see the progression. We want to see people take that step forward. I know it's easy to do nothing. It is easy to do nothing, but it's rewarding to take that first step. So I know I'm up against the clock here. Everyone's ready for lunch. I wanted to say thank you to all the folks from OTEC, from Lisa Hall, Victoria Beal, Paula Hyman, Becky Humphries for moderating our presentation. I've done several of these, and this has been one of the best run, most organized presentation. I look forward to hopefully seeing you all in person next year. If everything goes the way it's supposed to go, we can do that. I thank you for your time, and I will open it now to any questions.
Okay, thank you. We do have a few questions we'll try to get through. The first one, can the rings be reused?
Well, yes and no. The frames can be reused. It depends on the wear. I hate to say reused. I mean, we work in an industry that we're making products that are designed to last for decades, which kind of is odd because we're working ourselves out of a job. That's why we have to continue to evolve and offer new products and find more solutions to existing problems. Frames can be reused, but that's a real broad stroke, depending on the conditions, depending on what they've been subjected to. I would say yes and no.
Okay. How do the composite castings hold up to salt and calcium chloride?
That's specifically what they're designed for. They are designed to not have any sort of bearing or impact when exposed to chemicals. H2S, hydrogen sulfide, that's one of the primary focuses for those castings. So they are designed to, besides being traffic rated, they are designed to resist that kind of corrosion.
Okay, great. Well, our time is up. We do have many other questions that will be emailed to you to get answers for each of these, but I just want to thank everyone for attending this session and thank you for all the great presentations.
Thanks, everyone. Have a great week.